The SPARQL query language. SPARQL is a query language for triple stores using the RDF data model. It is an acronym for SPARQL Protocol and RDF Query Language, pronounced SPARQL. It predates Cypher, and since Cypher's pattern matching is borrowed from SPARQL, they look quite similar. The same query as before. Finding people who have moved from the US to Europe is even more concise in SPARQL than it is in Cypher. See example 2-9. Example 2-9. The same query as example 2-4, expressed in SPARQL. The structure is very similar. The following two expressions are equivalent variables. Start with a question mark in SPARQL. Because RDF doesn't distinguish between properties and edges, but just uses predicates for both, you can use the same syntax for matching properties. In the following expression, the variable USA is bound to any vertex that has a name property whose value is the string United States. SPARQL is a nice query language. Even if the semantic web never happens, it can be a powerful tool for applications to use internally. Roman 8. Datalog and Datalog use a Clojure S expression syntax for Datalog. In the following examples we use a prolog syntax, which is a little easier to read, but this makes no functional difference. Graph databases compared to the network model. In our document Databases Repeating History, on page 36 we discussed how codicil and the relational model competed to solve the problem of many-to-many relationships in IMS. At first glance, codicil network model looks similar to the graph model. Are graph databases the second coming of codicil in disguise? No, they differ in several important ways. In codicil, a database had a schema that specified which record type could be nested within which other record type. In a graph database, there is no such restriction. A vertex can have an edge to any other vertex. This gives much greater flexibility for applications to adapt to changing requirements. In codicil, the only way to reach a particular record was to traverse one of the access paths to it. In a graph database, you can refer directly to any vertex by its unique ID, or you can use an index to find vertices with a particular value. In codicil, the children of a record were an ordered set, so the database had to maintain that ordering, which had consequences for the storage layout, and applications that inserted new records into the database had to worry about the positions of the new records in these sets. In a graph database, vertices and edges are not ordered. You can only sort the results when making a query. In codicil, all queries were imperative, difficult to write, and easily broken by changes in the schema. In a graph database, you can write your traversal in imperative code if you want to, but most graph databases also support high-level, declarative query languages such as Cypher or SPARQL. The foundation, Datalog. Datalog is a much older language than SPARQL or Cypher, having been studied extensively by academics in the 1980s. It is less well known among software engineers, but it is nevertheless important, because it provides the foundation that later query languages build upon. In practice, Datalog is used in a few data systems. For example, it is the query language of Datalog, and Datalog is a Datalog implementation for querying large datasets in Hadoop. Roman 8 Datalog's data model is similar to the triple store model, generalized a bit. Instead of writing a triple as subject, predicate, object, we write it as predicate subject, object. Example 2-10 shows how to write the data from our example in Datalog. Example 2-10. A subset of the data in figure 2-5, represented as Datalog facts. Now that we have defined the data, we can write the same query as before, as shown in example 2-11. It looks a bit different from the equivalent in Cypher or SPARQL, but don't let that put you off. Datalog is a subset of Prolog, which you might have seen before if you've studied computer science. Example 2-11. The same query as example 2-4, expressed in Datalog. Cypher and SPARQL jump in right away with select, but Datalog takes a small step at a time. We define rules that tell the database about new predicates. Here, we define two new predicates, within recursive and migrated. These predicates aren't triples stored in the database, but instead they are derived from data or from other rules. Rules can refer to other rules, just like functions can call other functions or recursively call themselves. Like this, complex queries can be built up a small piece at a time. In rules, words that start with an uppercase letter are variables. and predicates are matched like in Cipher and SPARQL. For example, name location. Name matches the triple name Numerica, North America with variable bindings location equals Numerica and name equals North America. A rule applies if the system can find a match for all predicates on the right-hand side of the colon operator. When the rule applies, it's as though the left-hand side of the colon was added to the database with variables replaced by the values they matched. One possible way of applying the rules is thus. One name Numerica, North America exists in the database, so Rule 1 applies. It generates within recursive Numerica, North America. 2 within USA, Numerica exists in the database and the previous step generated within recursive Numerica, North America, so Rule 2 applies. It generates within recursive USA, North America. 3 within Idaho, USA exists in the database and the previous step generated within recursive USA, North America, so Rule 2 applies. It generates within recursive Idaho, North America. By repeated application of rules 1 and 2, the within recursive predicate can tell us all the locations in North America or any other location name contained in our database. This process is illustrated in Figure 2-6. Figure 2-6, determining that Idaho is in North America using the Datalog rules from example 2-11. Now Rule 3 can find people who were born in some location born in and live in some location living in. By querying with born in equals United States and living in equals Europe, and leaving the person as a variable who, we ask the Datalog system to find out which values can appear for the variable who. So, finally we get the same answer as in the earlier Cipher and SPARQL queries. The Datalog approach requires a different kind of thinking to the other query languages discussed in this chapter, but it's a very powerful approach, because rules can be combined and reused in different queries. It's less convenient for simple one-off queries, but it can cope better if your data is complex. Summary. Data models are a huge subject, and in this chapter we have taken a quick look at a broad variety of different models. We didn't have space to go into all the details of each model, but hopefully the overview has been enough to whet your appetite to find out more about the model that best fits your application's requirements. Historically, data started out being represented as one big tree, the hierarchical model, but that wasn't good for representing many-to-many relationships, so the relational model was invented to solve that problem. More recently, developers found that some applications don't fit well in the relational model either. New non-relational NoSQL data stores have diverged in two main directions. Document databases target use cases where data comes in self-contained documents and relationships between one document and another are rare. Graph databases go in the opposite direction, targeting use cases where anything is potentially related to everything. All three models, document, relational, and graph, are widely used today, and each is good in its respective domain. One model can be emulated in terms of another model. For example, graph data can be represented in a relational database, but the result is often awkward. That's why we have different systems for different purposes, not a single one-size-fits-all solution. One thing that document and graph databases have in common is that they typically don't enforce a schema for the data they store, which can make it easier to adapt applications to changing requirements. However, your application most likely still assumes that data has a certain structure. It's just a question of whether the schema is explicit enforced on write or implicit handled on read. Each data model comes with its own query language or framework, and we discussed several examples: SQL, MapReduce, MongoDB's aggregation pipeline, Cipher, SPARQL, and Datalog. We also touched on CSS and XSL/XPath, which are database query languages, but have interesting parallels. Although we have covered a lot of ground, there are still many data models left unmentioned. To give just a few brief examples, researchers working with genome data often need to perform sequence similarity searches, which means taking one very long string representing a DNA molecule and matching it against a large database of strings that are similar, but not identical. None of the databases described here can handle this kind of usage, which is why researchers have written specialized genome database software like GenBank. Particle physicists have been doing big data-style large-scale data analysis for decades, and projects like the Large Hadron Collider LHC now work with hundreds of petabytes. At such a scale, custom solutions are required to stop the hardware cost from spiraling out of control. Full-text search is arguably a kind of data model that is frequently used alongside databases. Information retrieval is a large specialist subject that we won't cover in great detail in this book, but we'll touch on search indexes in Chapter 3 and Part Roman 3. We have to leave it there for now. In the next chapter, we will discuss some of the trade-offs that come into play when implementing the data models described in this chapter. XML data in SQL Server 2012 documentation, technet.microsoft.com, 2013. PostgreSQL 9.3.1 documentation. The PostgreSQL Global Development Group, 2013. The MongoDB 2.4 Manual, MongoDB, Inc., 2013. RethinkDB 1.11 documentation, rethinkdb.com, 2013. Apache CouchDB 1.6 documentation, docs.couchdb.org, 2014. Rick Long, Mark Harrington, Robert Hain, and Jeff Nichols. IMS Primer, IBM Redbook SG 24-5352-00, IBM International Technical Support Organization, January 2000. Stephen D. Bartlett, IBM Zims Myths, Realities, and Opportunities, The Clipper Group Navigator, TCG 2013015 Li, July 2013. Amarawadala, Schemon Reed VS, Hemon Wright, at Berkeley XRAD Lab Retreat, Santa Cruz, CA, May 2009. Martin Nodersky, The Trouble with Types, at Strange Loop, September 2013. Conrad Irwin, MongoDB Confessions of a PostgreSQL Lover, at HTML5 DevConf, October 2013. Percona Toolkit Documentation, Petty Online Schema Change, Percona Ireland Limited, 2013. Rainy Keto, Tobias Bielalock and Tobias Schmidt, Large Hadron Migrator, SoundCloud, 2013. Shane C. Corbett, Jeffrey Dean, Michael Epstein, et al. Banner, Google's Globally Distributed Database. A 10th Usenix Symposium on Operating System Design and Implementation OSDI, October 2012. Donald K. Burleson. Reduce I/O with Oracle Cluster Tables, dblayoracle.com. Fei Chang, Jeffrey Dean, Sanjay Gemawat, et al., Bidable, a distributed storage system for structured data, at 7th Usenix Symposium on Operating System Design and Implementation OSDI, November 2006. Bobby J. Cochrane and Kathy A. Manite. DB2JSON Capabilities, Part 1, Introduction to DB2JSON, IBM Developer Works, June 20, 2013. Joseph M. Hellerstein, The Declarative Imperative, Experiences and Conjectures in Distributed Logic, Electrical Engineering and Computer Sciences, University of California at Berkeley, Tech Report UCB/EAKS 2010-90, June 2010. Jeffrey Dean and Sanjay Gemawat, MapReduce, Simplified Data Processing on Large Clusters, at 6th Usenix Symposium on Operating System Design and Implementation OSDI, December 2004. The Neo4j Manual v2.0.0 Neo Technology, 2013. Emily from Twitter Correspondence, January 3, 2014. David Beckett and Tim Berners-Lee. Turtle, Terse RDF Triple Language, W3C Team Submission, March 28, 2011. Datomic Development Resources Metadata Partners, LLC, 2013. Apache Gina, Apache Software Foundation. Steve Harris, Andy Seaborn, and Eric Pratamo. SPARQL 1.1 Query Language, W3C Recommendation, March 2013. Fonz Raidmakers, Route for Big Data Analysis, at Workshop on the Future of Big Data Management, London, UK, June 2013.